Okay, so not every curve or not every relation is a function. We said just the other day that a relation is a function if and only if what? There's different ways to say this.
A vertical line only passes through it once.
Yeah, exactly. So you can use the vertical line test, right? So that's what we're going to write down. But that essentially means a function is a machine. It's a machine that takes things that you throw into it. I like to think of this. If that's the function f, I take x guys that I throw into it, it grinds them all down, and it pops out y guys. How many y guys come out for each thing you plug in, though?
One.
Only one. It doesn't make sense that you throw something into your machine and two things pop out. How are you going to decide like which one's supposed to pop out when? That's why functions are pretty important right later on, okay? That's why the vertical line test says you're a function if and only if a vertical line touches only once. If it touches twice, you're getting two different things out of your machine. That's not good. Okay? Killian, get notes out. Take this down. Last time I warned you. Okay. So what we're going to do today is learn something new. If you have an inverse relation, if you recall, we didn't do this heavily, we're going to look at it a little more today. You form an inverse graphically, like with a picture, by reflecting over this diagonal line. So, let's say we had like a piece of a parabola. Let's call that f. The way I find the inverse function for f is I reflect it over this line. This is line y equals x. That's where inverses come from, like with a picture. Okay? So what's it going to look like? How am I going to draw it? If I reflect it. Yeah, like this, right? What's that look like? Which function?
Square root of x.
Looks like square root of x. This looks like half of x squared, doesn't it? Right. So there's an idea. And remember, we notate f inverse by saying f raised to the -1. That's the notation. You can only use that notation if indeed your inverse is a function. Sometimes your starting thing's a function and your inverse is not. It just depends. So we need a rule that says, okay, the inverse relation for any inverse thing that you draw, when's that a function? Because the vertical line test isn't going to tell you that. The inverse is a function if and only if, let's see how I can say this, f, the original, passes the horizontal line test. So horizontal line has to touch f only once if the inverse is going to be a function. You might still be able to find the inverse, but it's not going to be a function if the horizontal line hits it twice. So let's look at some pictures, okay? This is all fine and a little abstract to talk about without pictures. Once you see pictures, it's not hard. So let's look at some different functions. And let's talk about each one. We'll decide if the original f is a function and if the inverse is a function for each one. Okay, so I'm going to just pick some different types of things. Pick that guy. That guy. That guy. Need to fit one more in here somewhere. Okay. And that guy. So, first of all, let's come up with the equations for each one of these, just to review a little bit, okay? What kind of function is this? Exponential. Could someone give me just a guess? I mean, we can't tell exactly what it is, but something it could be. Growth or decay? Growth, so like 1 to the x, I don't think we ever saw that, did we? Exponentials can't be 1, base can't be 1. Then it'd just be a line. 0.5?
Over 9,000.
How about 2 to the x? Or 3 to the x, or something like that, okay? How about this? You guys help me build this function. Let's say it's been shifted down this way 1 and over that way 2. What's g of x? That's the parent, yeah. Negative something squared.
Oh, 2. No.
Minus 2 inside or outside?
Inside. That's 2.
That's right, 2.
And then minus 1 and that's
Good.
Could we write that in original instead of writing it
This one. We don't know how to say this one exactly, but it's kind of like x to the 3rd, isn't it? Or like 7th, something odd. And it looks like it's been shifted and stuff. So let's just say like x to the odd something.
something or something.
Okay?
Yes.
We haven't really studied that much yet. This one, what's this?
Wait. What? So x to the odds.
We don't know exactly what it is. This is an ellipse, right?
Out of those.
So how do ellipses look? Equals what?
1.
1.
Over.
How far does it go in the x direction?
3.
3, so we go x squared over
9.
plus or minus
Plus
plus. It's an ellipse, not a
x
hyperbola.
squared over, or y squared, sorry, over 16.
So it goes out 4 in the y direction, right? Okay, so we got all those done. Now, that's the old stuff. Let's review. This one, is the original a function? Is that thing a function?
Yes.
Passes vertical line test, yes. Morgan, watch. Okay. Is the inverse a function? I can't see the inverse. Yeah, we could try to draw it, but we don't need to draw it. Just pass the horizontal line test.
Yes.
Yes, it is. So I can't even see the inverse, but I know it's a function. How about this one? Is that a function? Is g a function? Yes. Is the inverse of g, whatever that looks like, a function?
No.
Not a function. So, would we be allowed to write, when we found the inverse, which we're going to do in a second, would we be able to write g inverse of x?
No.
Can't do that. What about this one?
Because if you flip it, it's going to not pass the vertical.
That's the way it's
No, it's not flipping up, it's flipping diagonal.
but it's
To flip it like that.
the
See, and then it wouldn't pass.
Then it would look like this.
Okay. Alright.
Yeah. Okay. This one, function?
Yes.
Is the inverse a function?
No.
It passes there, but right here, it's at 3 times. So definitely not a function if you find the inverse. Okay. This one, either one of them isn't a function. No, no. Okay? There we go. Alright, so let's actually go about finding an inverse now.
Can the inverse be a function but not the original?
Yeah, but either one could be a function.
I think an inverse.
They didn't. There's no rule that says that one has to be or the other has to be or they both have to be. Nothing like that. Okay.
Okay.
Okay. So let's find this one. Let's say we have the cube root of x plus 1. That's that cube root thing that's been shifted left by 1, right? Okay. So let's find the inverse, and then let's decide if it's a function. And we'll find the domain and range on it too. So here's the strategy. If you don't have the drawing to go about drawing the inverse, that's not the easiest way actually. Drawing it's tough sometimes. Here's what you do. You go about this the same way that you would with the drawing. What's reflecting over that line y equals x mean? It means, well, first of all, writing this as y. And when I actually do that reflection and flip it, I'm switching what? When you reflect over that line, what are you switching? You're switching the x and y. So I'm going to put x here and y there. I switch the x and y. And then I solve for my new y. So if I want to solve, what do I do to get rid of that cube root? Cube it. And then if I want to solve, what do I do next? Subtract 1. And there we go. Michelle, yeah.
Why do you switch the
Inverse.
Well, this goes back to algebra 1. Like if you have an ordered list of points, the way you find the inverse is you flip those points. You switch the x and y values. If you're thinking about the picture and inverting this over the line, let's say you have that f, just like we did a second ago, and that f inverse. This point gets changed to this point,
See how they change.
and this point has like, let's say it's like 2, 1, then this point is 1, 2. Does that make sense? That's kind of the theory on where it comes from. Good question. Okay, so we could graph that, because I want to decide, can I write it as an inverse or not? So if I graph that, that's the snake curve that's been shifted down 1. So you guys tell me, is that a function?
Yeah.
So can I call this f inverse? I can. So I can name this f inverse of x. This guy is f inverse. Okay? Let's do one more together and then I'll let you guys try one yourself. Let's say we have this guy.
But the original of that function is not the original is not.
The original of this, if you draw it, looks like this. Left
Or
1.
is it a function? So
Does that
it's
pass the vertical line test?
Yeah.
So it's a function too, and we could have seen this by looking at that the inverse was going to be a function. Okay?
Gotcha.
This one, same strategy. Let's go through it one more time together before we get the hang of it, okay? So I'm going to write down y equals. I'm going to then switch. So I'm going to put x here, y there. Trying to color code it so you guys can see it a little easier. And then I need to solve for y. So how do I get rid of what I need to do first? Square root, right? Gotta get rid of that. When I use the square root,
Plus or minus.
plus or minus. Then I'm going to subtract 2. I'm going to multiply by 2. So I get -4 plus or minus 2 root x. That's some kind of square root. How many different things is this though?
Two.
This is two different things, isn't it? So we could graph like a positive square root and then a negative square root. Think about what this picture is
But
going
it
to look
only
like.
goes to the top.
They've both been shifted down 4, right? So they both start from like that. Y equals positive root 2 root x minus 4 is going to look like that. The negative root is going to look like that. So you guys tell me, is this thing a function?
But I thought you couldn't have negative. No.
Definitely not, because it hits twice. The vertical line test shows it's not a function. If we had drawn this, what kind of thing is this? What kind of function? It's a parabola, isn't it? I mean, it's going to be some kind of shifts and stuff, but it's some kind of parabola which looks like that. Is it a function? Yes. Is its inverse a function? No. We just saw that. Okay? So this is a little bit more complex than what we've been doing. You guys try this one. Find the inverse of x to the 4th plus 7, and then also tell me the domain and range. If you need some help, ask me. So you want to look at the domain range till after you've got the thing. Just look at the picture.
So this one, it doesn't matter though. It doesn't matter how big.
Pretend it's where there's graphic, but it's been shifted where. Alright, so okay, so you should have y equals x to the 4th plus 7, then I switch. I solve for the new y by subtracting 7 first. How do I get rid of 4th power? I use the 4th root. Since it's even, I need a plus or minus. If it was odd, wouldn't need plus or minus, right? So I get y equals plus or minus this 4th root of x minus 7. I can think about graphing that. Just because it's a 4th root, don't get scared. It's just like any even root. What's square root look like? Trace it in the air for me. It's like this, right? Okay, that's what any even root looks like. Where's it been shifted?
Down 7.
It's inside.
Right, 7.
Right, 7. So the positive looks like that. And then what else do I need? The negative, which looks like that. So you guys tell me, can I write this as equal to H inverse?
No, it's not passing the vertical line.
That's not a function,
Why isn't it a function?
because it doesn't pass the vertical line test. And if you had drawn this, this looks like x to the 4th plus 7, right? It's a real skinny guy. Does it pass horizontal line test? No, that told you that thing wasn't a function already. You didn't have to do that, but. So, looking at this, domain and range, what's the domain? X values, what do we got? The smallest one is
Anything greater than 7.
7. So 7 to
Infinity.
infinity. What's here?
Parenthesis.
What's here?
Bracket.
Bracket, because that's like a filled in dot. And the range?
And they all.
It looks like it's flattening out because I suck at drawing, but it's going down. So, all real numbers, yeah. Okay. We have one last thing to look at today.
No, I don't have room.
Just in the air.
Don't
you see it? Don't you see it?
What? I did it like 6 times.
It makes so much sense. Just fill in the back and makes me tired.
Killing me.
I know.
Ruining
Okay,
my-
so the last thing we're going to do, what we learned in the last section, that composition operation, one of its purposes, just one, it's used for tons and tons of stuff. One of its purposes is to check whether functions are inverses or not. So, there's this theorem. It's a pretty simple theorem. Here's what it says. It says if both f of g of x and g of f of x, if they both equal x, this is all about that reflection line that Michelle asked us about, right? If they both equal x, then f and g are inverses. So you can use this to check if things are inverses if you're not sure. It's a powerful tool. So let's say we've got these two candidates and we want to say are they inverses or not. Just looking at them, what do you guys think? Do those look like inverses? They look like they'll undo each other? They look pretty good to me. Let's see. So we're going to go f of g of x. So that means I'm taking this, excuse me, taking this one and putting it in that one. So I'll have 3 times 1/3 x plus 1 minus 1. So you get x plus 3 minus 1. Are the inverses? No. Do I even need to check g of f? No, because one of them already failed. So, not inverses. Therefore, these triple dots mean therefore. Therefore, f and g are not inverses.
That's funny. Wait, so if they were inverses, what would the answer be?
We're going to say
Yeah.
they have to be x. They both have to be x. Exactly. Okay, let's try the last one for today. I'm sorry to make this so long today, but we need to get done.
You need to keep your notes to one page.
multiple classes I've taken 5-6 pages of notes and teeny tiny writing. An hour. I'm sorry. And Bertha. Okay, same thing. I'm gonna check it one way and you guys are gonna help me the other way. So f of g. Try to color code to help you out. So I'm gonna be putting this in that X spot. Remember, if there's more than one X spot, you gotta put it in all those spots, right? So I'm gonna just put it in there. Can somebody help me simplify that just a little bit? You saying it, Aislinn? I can't hear.
Can you just get rid of these around?
You can get rid of the ones, yes. Okay.
And then you
That's left.
multiply x by x over 1.
You flip it, right? So, looking like they might be inverses.
That
It
could
is.
be opposite.
But sometimes it'll work one way, not the other if they're real close. It just happens that way. So you gotta try the other way. So you guys try this way real fast. It's not gonna take much. Do g of f, see if that's x. If it is, they're inverses.
Yeah. Oh my gosh. I don't know. You said. I'm just nice.
Okay, so we should have gotten. We put f in there. We get 1 over f. We got a +1 going on. So then we flip that. And we say, oh, cancel. X. Okay. So we could say f compose g equals g compose f equals x. So f and g are inverses. Or you could say something like g of x equals
G inverse of x.
close.
F of x equals F inverse of x.
That's true, right?
Why not?
Okay, that's it.
Did you
This
catch that? Or did it bounce?
I-
Did that bounce? Did you catch it?
it bounced and I caught it.
Oh, dude, it's so
This is the one that's due Monday, guys. So it's due Monday.
What if I have questions?
You would get Mr.